Exercise 3.6 on the exponential and logarithmic functions on page 116 of your textbook. I am kind of combining with a previous exercise. I believe it might have been 2.4 on solving exponential and logarithmic equations. Just because you did that over the holidays, you might have forgotten it till now. We will be covering, of course, using the index laws and the logarithmic laws. Make sure that revise over those are very important. And also converting between exponentials and logarithms. Also, generally speaking, the graph of an exponential and what it looks like, and also the nature of a logarithmic graph as well. I can never say that word. Alright, so what I'm going to do is I'm actually going to make sure that we understand our index law and logarithm laws. First thing is these laws right here. Have them in your notebook, but also know them off by heart, right? You don't need to know, for example, I'm never going to, whoever is examining you will never say, recite index law number 3, right? It doesn't matter, as long as you know how to use them. You'll never need to write out the formulas, you'll never need to specify or know which rule is called what rule, you just know how to use them, okay? And it's very important because the logarithm laws are the direct opposite. So things like, for example, multiplication, where you've got the same base. I'm not going to cover that. I'm assuming you already know that. If you don't, please go back and complete the previous exercise. It'll be on the weekly outline. I'm going to pick a couple of choice ones that are quite difficult, or at least not obvious at first glance, and we'll do those ones together. I'm going to start off with question. So example 1, I'm going to start with example 2. Example 1, I'll let you do afterwards as well. So again, that's just your basic laws. But example 2, we're going to go through these ones together. This one says 9 to the power of x equals to 12 times 3 to the power of x minus 27. The tricky part here is that when you work with index laws, a lot of us tend to look very streamlined, apply only index laws, right? But a question like this actually encourages us to use a different format. I am going to apply my index laws, of course, but I'm going to try and make everything under a base of 3. Right? That just makes sense to me because I've got 9, 3, 27. I'm going to rewrite this as 3 to the power of 2 to the power of x equals to 12. I'm going to zoom in a bit, actually. Times 3 to the power of x minus 3 to the power of 3. Moving everything to one side, and hopefully you might be able to see a pattern of what I might do in the future now. I'm going to write 3 to the power of x squared. Are we okay with that being the same thing? Yeah, good, because they're multiplied anyway. I'm going to subtract 12 times 3 to the power of x, and I'm going to minus 3 to the power of 3, which equals 0. Now in this circumstance, sorry, not minus, plus. In this circumstance, 3 to the power of 3 is fine. 27 might be a bit easier, but I'll move on. I'll show you why in a moment. Does anyone know what I'm about to do? Does it seem quite familiar? What am I going to do? What am I going to do?
Say, introduce like U.
Perfect. You're going to introduce a letter. Now, I'm going to avoid using U just because U is typically, I use it for chain rule, so let's just use A, for example. I'm going to write let A equal to 3 to the power of x, and we get A squared minus 12A, and I'm going to change that back to 27 because that's a nice quadratic function. Good. Cross method, of course. A here, multiply what numbers multiply to give me 27, add to give me negative 12, negative 9 and negative 3. Right? Which means I get an answer of, I'm a little bit wary of space, I might just write it up here. I get A minus 9, A minus 3 equals 0. Of course, that means that A equals to 9 and A equals to negative 3. Now, of course, we're not done yet. So not negative 3, positive 3. Of course, we're not done yet because you have to substitute back, because A we've just made up ourselves, right? So we have to substitute back and we end up with 3 to the power of x equals to 9, or 3. Of course, 3 to the power of what gives us 9? X equals to 2, or 1. It's a little bit of a different approach, but it is entirely accessible, so I definitely recommend you understand this approach. Slightly different approach, but again, something that's a little bit different. I'm going to go through question B. 27 times 3 to the power of n equals 27 to the power of n times 3 to the power of 1 over 4. Okay, so I'm going to expand first. I'm going to end up with 27 to the power of n times 3 to the power of n squared, there we go, equals 27 to the power of n times 3 to the power of 1 over 4. Now, I'm going to show you the dumber long way I did this for some reason, right? And then I'll show you the easier way to do it, okay? The longer way I'm doing it here is I'm just going to go ahead and write 27 to the power of n is the same as 3 to the power of 3 to the power of n, or 3 to the power of 3n, times 3 to the power of n squared equals to 3 to the power of 3n times 3 to the power of 1 quarter. Of course, I'm multiplying, so I can just add them together. That means 3 to the power of 3n plus n squared equals to 3 to the power of 3n plus 1 quarter. And then you can equate the powers because the bases are the same. We end up with 3n plus n squared equals to 3n plus a quarter. Seems a bit redundant, doesn't it? Does anyone know what I could have done earlier? Yeah.
3 to the power of n squared equals 3 to the power of 1.
Good, I can just cancel these, can't I? Can't I just divide both sides by 27 to the power of n? You're not taking a shortcut, you're just working more effectively. Then we end up with 3 to the power of n squared equals to 3 to the power of 1 quarter. In which case, again, we equate the powers. N squared equals to 1 quarter, which means that we have n equals to 1 over 2. What have I done wrong? Plus or minus, thank you very much. Well done. Okay. So when we're looking at exponential functions, we're focusing on the idea that it can look something like y equals to some number to the power of x. Later on, I'll give you a specific number. So for example, e, right? But for now, we're focusing on just some number. If we have, for example, something that looks like y equals to, and I'm going to separate this out, y equals to, 2 to the power of x, the idea is that graph, as you increase the value of x, it, hence the name, exponentially increases as you increase the value of x. Right, 2 to the power of 3 is significantly smaller than 2 to the power of 4, right? And that gap is again significantly smaller than 2 to the power of 5. You get the idea. However, if we work backwards, right, as your x value decreases into the negatives, right, into the negatives, the value never becomes negative. So 2 to the power of negative a billion is still a positive number. Because remember, it's the same as saying 1 over 2 to the power of a billion. Okay? So a graph never reaches y equals 0. So a function that looks like this should always... Oops, that was not asymptotic behavior. Right? So never go back down into up. That is not asymptotic behavior. It should be something like this. What is this value right here? What is my y-intercept? When I let x equals 0, I get 1. Yeah, remember anything to the power of 0 is 1. And of course, and this is something that we don't typically talk about as much, every time you have an asymptote, even if it is the axis, you can just write y equals 0. That is your your asymptote equation, you must write that as well. Okay. Of course, transformations apply. It is very common practice for us to apply transformations to these kinds of questions. Things like, what happens if I have x minus 1? If I have x minus 1, it's the same as saying f of x minus 1. So I shift 1 unit to the right. Yeah? The same transformation rules apply for exponentials as they do for our other polynomials as well. Any questions? Okay. Let's move on. Logarithmic laws. Hopefully we are also familiar with them. Remember, they are the opposite of our exponential laws, namely because they are inverse. So things like these laws right here, this one is very less commonly used, but please remember it is an option that you can use. Okay, if you've got log base a to the power of b, then you can use a different variable, different value, for the same constant both sides and keep it this way. Okay, I'm going to jump straight ahead to question, what is this, 3b. And then I'll move on to another question. We'll do one more there. I'll do my graph explanation and I'll let you get started finally. So applying the log laws, of course, we need to make sure that we know that we can shift the coefficient. If we shift the coefficient, we can make it a power, right? So that will be this law right here. Okay, of course it works both ways. So we can rewrite this as log base 10. Remember, even if it's base 10, we have to specify base 10. Now it's 3, right? Because I'm moving this value up to the front, or sorry, from the front, it becomes 3 squared. I'm just going to write 9. Plus log base 10 of 16 minus, and instead of writing the 2, I'm going to write log base 10 of, and I'm going to square the value on the inside, which becomes 36 over 25. This is a very classic exam question. There are a lot of things that we can do to make sure we get the correct answer, but things that we can do to make sure that we get the correct answer in a shorter time frame. Welcome. Of course, if we're working with the opposite of exponential rules, when we add, we multiply what's inside the brackets, so that becomes log base 10 of 9 times 16, which I know off the top of my head is 144, my apologies. And then we still have the log minus log base 10 of 36 over 25. Exponentials booklet, page 16. Baby. Exponentials booklet, page 16. Of course, if we're subtracting, we can divide, right? Now, I'm going to use notation that might be a little bit confusing. If you want to take this step by step, you're more than welcome to. I'm just going to write log base 10 of 144 divided by a smaller fraction here. Now, I'm taking a couple of shortcuts. Remember that, for example, and you don't have to write this down, a over b all over c over d equals to ad over bc, right? And that is just stemming from the fact that when you multiply, you stage change flip. How nostalgic. Okay? I'm going to skip that step, and I'm just going to rewrite it as log base 10 of, and I'm multiplying the top and the bottom, 144 times by 36, not 36, 25, over 36. Now, most students, I should not say most students, a lot of students will then take the time to go 144 times by 25, because this is a non-calculated question. 144 times 25, what does that equal to? And then divide that by 30. Don't do that. Use your basic simplification, your fraction simplification method, right? What goes into both 144 and 36? Of course, 12. That becomes 12. That becomes 3. And we end up with log base 10 of 12 times 25. It's a bit annoying. Why don't we simplify it a bit further? So I'm going to cross that out. That becomes 4. That becomes 1. And we get 4 times 25, which is 100, over 1. I'm not going to bother writing as a fraction. And I'm going to write 100. Sweet. Happy? You know every time I say that, we're never happy. Why am I not happy, Alex?
Because log base 10 to 100 is...
Exactly right. It's a expected easy simplification. 10 to the power of what gives you 100? Of course, that is 2. So we end up with an answer of 2. Ooh, how are we feeling? This feels nostalgic, difficult, traumatizing, any of the above? Okay. I'm going to move on to, I'm going to skip quite a number of them. I'm going to jump to example 4D. It is a very unique type of question, but I think it is a very good question because it has come up in exams before. 0.7 to the power of x is greater than or equal to 0.3. The problem with this one is, of course, a greater than or equal to symbol. It's very confusing. Rather than trying to rearrange it, I'm just going to take the log of both sides. Now, it doesn't matter what log because we're just keeping it consistent. I'm going to write log equals to log base 10 of 0.7 to the power of x is greater than or equal to log base 10 of 0.3. And you know what? I don't like the fact that I've got an equal sign. Why do I not like that? Well, because there's an equal sign in the middle, right? Theoretically, that greater than or equal sign is kind of like an equality sign. I'm saying that these two are the same. They're obviously not, right? So make sure you don't make the mistake of using incorrect equal signs. Just add an arrow. Make it easier. Next line. Using my exponential laws, I know that because it's a power, I can bring it to the front. it becomes x times log base 10 of 0.7 is greater than or equal to log base 10 of 0.3. Again, the base doesn't actually matter in this case as long as you keep it consistent. We're doing the same on both sides. Then we divide both sides, and I'm going to do something incorrect, right? Feel free to watch what I do, and then I want you to try to figure out why I've done it wrong, or what I've done wrong. Okay, it's a very common mistake. I'm going to divide both sides by log base 10 of 0.7, so then it becomes x is greater than or equal to log base 10 of 0.3 over log base 10 of 0.7, and that's because, I mean, I'm not expecting, this is an exam 1 question, I'm not expecting you to do log base 10 of 0.3. I'm done. What have I done wrong?
Log base 10 of 0.7 is included in
Correct. Log base 10 of 0.7, there we go. This one right here, right, exclude the x. 10 to the power of what gives you 0.7? If it's 0, you get 1. If it's anything positive, it'd be 10 or greater than 10, wouldn't it? 10 to the power of 2, for example, is greater than 10. So anything below 1 as an answer. So if, for example, log base 10 of something below 1 is going to be a negative value. And if it's a negative value, of course we have to reverse the sign. So that becomes x is less than or equal to that fraction. Okay. Last bit before I get you to get started. Jeez, I've been talking for 30 minutes. Okay, so logarithmic graphs, of course, we're working with the inverse of our exponential graph. So before, I'm going to put, for example, y equals to, I don't know, I'm just going to use a. Y equals to a to the power of x, right? It looks like that. You've got your asymptote. It's a horizontal asymptote and exists when we have not applied transformations on the axis y equals to 0. Of course, because we are reflecting across the y equals to x line, right, that's an inverse, our function of our logarithm becomes something that looks a bit like this. Of course, depending on what your actual value is, it looks something like this, right? You know what, I'm going to move this one here so it's just shy of the axis. There we go. And this one should be like that. Hopefully yours looks a bit better than mine. Of course, because it's inverse, right, we're flipping across the y equals x line, your asymptote is no longer horizontal, it is now a vertical asymptote, right? Again, none of this stuff here, okay? A lot of students do this. You will lose marks over the dumbest stuff. Please don't do that, right? Must resemble asymptotic behavior. Any time where you're working with asymptote that's not on your axis, or even if it is really, you should be using a dotted line to symbolize that axis and so an axis, the asymptote, and labeling x equals 0, x equals whatever it is. The same transformations apply, yes?
So whenever you're labeling a graph with an asymptote, you always have to state the asymptote no matter what the question.
Correct. You must always state the equation of the asymptote, right? Most times, because it's a basic transformation from our original, so for example, if you had y equals a to the power of x, it's just going to be y equals 0. You might have plus 1. That would change your asymptote. But any horizontal translation would not change your asymptote equation for an exponential equation. Yeah? Whereas a horizontal translation for our logarithmic function would change it because it's a vertical asymptote. Any questions? Of course, our domain of our logarithm is restricted, right? It cannot be a negative value, and the same thing applies for our range, of our exponential value. A quick reminder: 10 to the power of nothing, or any number to the power of nothing, I shouldn't say any number, any positive number to the power of nothing can be a negative value. So if you have, for example, log base, I'm going to use 10 for example, of a here, a must be greater than 0. Can it be equal? Must be greater than 0. Okay. Again, I'm prophesizing that you'll see a question along the lines, that's a good pun, of trying to find the domain of some sort of question. Good idea to know that the log, right, inside cannot be a negative value. Any questions? Okay.